solutions that we find to the heat equation are going to be similar to those that we expect in general for parabolic PDEs, okay? So what is the method that we can use to get the fundamental solution? Well, it essentially relies on observing just a couple of things about the heat equation itself, okay? Starting in 1D. In particular, the symmetry that this equation has, that it's translationally symmetric, and also there's a particular self-similarity that solution should have in order to obey the heat equation operator, which involves a first derivative in time and a second derivative in space, okay? So again, we're going to require boundedness of u and ux, okay, as x goes to plus and minus infinity, okay? So we don't, in principle, have any hard boundary conditions except just that u and ux go to 0, okay? And the solution that we will get will be integrable also. So it's bounded and with respect to integrability, okay? And the first step in this process, okay, of getting a solution is to observe that if we make a change of variables, t prime equals a squared t, and x prime equals ax, for some constant a greater than 0, okay, then I make the following changes of variables to the operators, okay? So essentially, dt of u is equal to a squared dt prime of u, right? Because t, if I differentiate t prime with respect to t, right, through the chain rule, then I get this extra factor of a squared coming out, okay? And dx squared of u, okay, is equal to a squared dx dot squared of u also, right? Because if I differentiate this with respect to the chain rule, then this factor of a pops out twice, okay? So I can always rescale time and space in this way, and whatever was a solution in the original coordinates will be a solution in the new coordinates, okay? So all of this says that in the new coordinates, right, I have ut prime is equal to k u x x prime prime. Sorry, I'm sort of smushing that there, okay? So all of this is to say that, if I can advance the slide, that both u of xt and u of x over a, t over a squared, okay, or vice versa, satisfy star, my original PD, okay, where this is my PD labeled star there, okay? So that's self-similarity, okay? It just says that we can make a change of variables and it should still satisfy the original PD, ignoring the initial condition for now, okay? Fine, okay? Well, what does that give us? Well, it tells us that the solution, whatever solution that we get, has to have that symmetry, okay? So we need a solution where if we plug in that change of variables, then the dependence of our function on those variables shouldn't change. We should get some sort of cancellation. Okay. So essentially, our self-similar solutions, okay, u of xt, okay, should depend on some function v of x over the square root of t. Okay. Why that? Well, if we go back here, right, remember that we said that we should be able to scale x by a, and we should be able to scale t by a squared. Okay. And so self-similarity tells us that if we want those scalings to cancel out, then our functions need to basically be of this particular argument, right? Because this is equal to, v of a times x divided by square root of a t squared, and so this is squared. So this will cancel with this, okay? And any scaling like that should always cancel out, okay? So if we substitute this into our PDE, right? And we say that y is equal to x over the square root of t, okay? And we work out basically the chain rule, okay, for each of these, right? Then we get that dt v of y is equal to dy dt times v prime, okay? And dy dt in this case is going to be equal to minus 1/2, right? 1 over t to the 3/2 multiplied by x. The x of v of y is going to equal dy dx v prime of y, and dy dx is just equal to 1 over the square root of t, and then dx squared of v of y is equal to 1 over the square root of t multiplied by, again, 1 over the square root of t, v prime prime of y, okay? So what we end up with, right, is that if, let's say that u of xt, right, is equal to some function, right, of t. So I'm going to introduce this scaling t to the alpha out front multiplied by v over the square root of t, okay? No, wait, sorry. Let me back up a bit before I motivate that. If u is just equal to this v of y, right, then dtu is going to equal minus x over 2t to the 3/2, okay? And this is going to be equal to K multiplied by 1 over T V prime prime of Y, okay? So this should be a V prime of Y. This is equal to K over T V prime prime of Y. Okay. And so this is equal to our dx, our K dx squared of U here. Okay. So our equation now for V is given by this this equation here, right? It has this additional term out in front here, but we can realize that that's x over square root of t equals y. So we can write that as minus 1 over t v prime of y times y is equal to k over t v prime prime of y. So these two things cancel here. Okay. But then the additional terms that we get there are going to come from assuming.
Did we drop a 2 in the denominator? On the left-hand side?
Yeah, you're right. Yeah. That should be right here. Right. Yeah. Okay. So if we, yeah, so if we assume instead, okay, that U is equal to some function T alpha V of Y, okay, then we can follow a similar process. So if U is equal to T to the alpha V of Y, and again we sub this into star or PDE there, then we'll end up with an additional term that looks like this this just V of Y term that we have here, right? So that'll come from the fact that, whoops, when I take this derivative d sub t of t alpha V of Y, right, I get a alpha t alpha minus 1 V term here, plus t to the alpha times this derivative term that we had here, right, which we worked out to be t to the minus 1. So then we have that t to the minus 1 term. And then we have, yeah, this additional 1 over 2 term here. So this minus y over 2 term here, v prime of y, okay, is equal to now this additional term here, right, k over t v prime prime, okay? And in particular, the way that we choose this alpha term, okay, I'll discuss in a minute, but it requires that we obey conservation. So we'll get to choose this power term for alpha so that the solution's integral is going to be positive, basically, for the whole, for all time, right? So that, you know, nothing leaks away over time as the solution starts to spread out. Okay.
Doesn't
So
this no longer obey self-similarity?
So the so we'll choose alpha so that this does obey self-similarity. Yeah, I see what you mean. So yeah, if you differentiate this with respect to, yeah, see if you make this change of variables.
Well, shouldn't there be another P alpha on the right-hand side? So then the T's would cancel out again.
Sorry, you're saying that, oh yeah, that's right. So the T to the alpha here, and then you have the T to the alpha minus 1 from there, right? Yeah, so then in that case, these T to the alpha minus 1s would cancel. And then you would end up, yeah, because this was your dx squared u term here. Yeah, sorry. So I need to finish this off. So then you get alpha v minus y over 2 v prime of y is equal to k v prime prime. And if we choose alpha to be minus 1/2, then we can rewrite this as k v prime prime plus y over 2 v prime plus v over 2. Yeah, so sorry, yeah. So as you're asking about, Kyle, so the self-similarity does still work out because you get this cancellation from the t to the alpha minus 1 terms.
But I mean, if we plugged in ax and a squared t into just u equals t to the alpha times v of y, we wouldn't get the same thing out.
Yeah, so it's okay if self-similarity is not satisfied at the level of scaling, right? Because we're not worried yet about satisfying initial conditions. It's just if there's any functional dependence on x and t aside from scaling, that needs to be self-similar. So it's okay for prefactors to not be self-similar because for any linear differential equation, you should always expect that you can rescale the differential equation. You can rescale solutions, and that should still be a solution, right? Just like with eigenvalue equations or something like that. You can always rescale eigenvectors, and those should still be eigenvectors of your eigenvalue problem. In this case, for any linear equation, I should be able to take, some prefactor here, and I should still be able to satisfy my original differential equation.
Okay.
And yeah, in this case, the t's cancel out okay, but it would just be, you would have this additional scaling factor, but that should be fine. Yeah.
Why aren't we happy with the equation right before this, like v double prime and v prime being there, but not, yeah, this one? Because can't we still solve this?
You can, but the problem is going to arise when you're trying to normalize your solution as the solution evolves in time. So like you're saying, Caleb, so it's fine. This equation's fine, right? This equation's fine for giving you a solution to the original PDE, but it's not going to be a solution that's properly normalized as you go forward in time. It's not going to integrate to 1 if you integrate in X. So the reason you sneak this scaling factor in, first of all, it's fine if you sneak the scaling factor in, because essentially, you know, any prefactor that you know, you can introduce and you still satisfy the ODE is legal in this case. But also you should be able to choose the scaling factor so that the solution is properly normalized. So that's why you introduce this weird additional scaling factor. Okay. Other questions? All right. So what we have now, right, is this ODE that we started with at the beginning of the class, right? And we know that V of Y is equal to A e to the minus y squared over 4k, okay? But we also have an expression for what y is, right? Remember, y is equal to x over the square root of t. So we could plug that in and we would get an expression in terms of u, okay? We can note that alpha equals minus a half, okay, works to normalize our solution, okay, because, okay, if we take u of xt is equal to 1 over the square root of t, now v of x over square root of t, okay, then we want, right, what is normalization ensure? It just ensures that whatever the integral of u is at the beginning of time, right, is not going to change. So its derivative with respect to t should not change, okay? In other words, that this integral u of xt dx is constant, okay? So essentially, the integral minus infinity to infinity, 1 over the square root of t v of x over square root of t dx, right, should be constant, okay? So in this case, right, if we take this integral, right, remember that if we set y equal to x over square root of t, okay, then we'll just have the integral, the minus infinity to infinity of just v of y dy, okay? And so indeed, this is going to be constant in t, right? So it basically accounts for the fact that when you take this integral, you need this extra factor of square root of t out in front, okay? So this implies that 1 over square root of t will properly normalize v of y, okay? So at the end of the day, what we have then is a form for our general solution, right? Which is that u of xt, right, is equal to 1 over square root of t, v of x over square root of t. And this is equal to a over square root of t, e to the minus x squared over 4k of t. Okay, 4k of t. Okay. So further, if I require, okay, let's say I want our fundamental solution, right, to integrate to 1, this yields the fundamental solution, okay? So the last thing that we have not specified is that constant a, okay? And of course, we can go through the process of, you know, integrating the Gaussian using this polar coordinates trick, you know, that you probably learned in calculus, right? And when you do that and you make this requirement, then your fundamental solution, which I'm going to call phi of xt, is equal to 1 over the square root of 4 pi kt e to the minus x squared over 4 kt. Okay? So what happens to this solution? Okay, well, something interesting happens as t goes to 0, right? Is that this prefactor is going to blow up. Okay, at t goes to 0. However, this is going to blow up too. So this is going to shrink to this is going to be e to the minus infinity essentially everywhere except at x equals 0. So as t goes to 0, your fundamental solution is going to concentrate. It's going to become more and more spiky, and essentially it'll become like a delta distribution at 0. And then it's going to spread out as you move forward in time, as you would think, you know, diffusion would. Okay, so this is our t equals 0 solution. This, you know, is t slightly beyond 0. This is t further beyond 0. And it smooths out more and more as time goes on. Okay, so as t increases, okay, you get a smoother and smoother solution over time. Okay, in Rn, right? Sorry, this is x, and then this is our phi of xt. In Rn, the procedure is similar, but now we have a vector argument in x. And in this case, we have that the exponential is in the magnitude squared of x divided by 4kt. Okay? So let me just recap that, right? Because, yeah, I got a little messy back there. Okay? So we started off by noting that U had to be self-similar, okay? And so any function that determined U would have to have an argument that depended on x over the square root of t, okay? However, because we have some freedom in choosing the prefactors of our function, okay, we could introduce a scaling in time that would allow us to properly normalize our function, okay? And we could have made that a general function, but we started off with a power function in P, okay? That probably seemed a little bit black magic-y, okay? We plugged in this assumption on the self-similar solution, okay? And in particular, when we introduced this scaling, we got an ODE that was the same as the one we introduced at the beginning of class that we worked through the method as to how to solve it, okay? We found that we got this sort of, you know, this Gaussian function. In addition, we noted that the proper scaling to take for the t power function was such that we had t to the minus 1/2. That would allow us to integrate our self-similar solution and have it always be, normalized to its initial value, okay? And then the last step was just to notice that if we want this normalized to 1, then we need this extra factor of, square root of 4 pi k in there, okay? So that's the fundamental solution to the heat equation. In Rn, this is going to satisfy ut equals k Laplacian of u, okay?